Today I talk about the recent development for the Kokkos-FFT library. I'm Yuichi and from Maison Simulation CA France, and this work is mainly done by the Seguza team, which is the CA internal project to get ready for the exascale computing with the usage of Kokkos ecosystem. So this is the outline of my presentation. Firstly, I'd like to introduce what is the typical use case of FFTs in the simulations and our effort to develop an interface between Kokkos and FFT libraries and to make it performance portably available. And we move on to the performance portable solution for distributed FFTs and then summarize our talk. So let's now start from the introduction. So we need performance portable solution for distributed FFTs. And there are many scientific applications relies on technically distributed FFTs. The left top is coming from the three-dimensional direct numerical simulations. And because of periodic boundary conditions, we can use FFTs for good accuracy and performance. In the middle, we have the plasma turbulence simulations. And this is simulation from CA and targeting the tokamak plasmas and dedicated to the very bigger nuclear fusion device called ITER. And in this kind of device, there is a periodicity intrinsically around these donuts. And this is called toroidal direction. So we have periodicity and we can use FFTs for that. Another example, and probably the most important one, is the molecular dynamics simulations like LAMPS. And there is the solver using FFT method. And obviously, we need performance portable solution because of the current HPC context, and they are fully dominated by GPUs and can be NVIDIA or AMD, or can be even Intel GPUs, and also need the good scalability. So preparation for the exascale system from in CA, and we have the many choices at the very beginning. Targeting the Jupyter machine, for example, or Frontier or Aurora, and these are coming from different vendors. And we are considering the directive or higher level abstraction-based approach like Kokkos or Shiko. But in the end, we choose Kokkos because in the Kokkos has nice features. The firstly, it is under the HPSF and the High Performance Software Foundation. So the software sustainability is kind of ensured. And also, it has the ecosystem like linear algebra or FFTs or tools or for profiling or even communications. So this is quite different than the other programming models. So let's now move on to the current existing distributed FFT solutions. There are multiple exist. So for example, in the Fortran and OpenACC solution, there are 2D comp and FFT library which supports CPU and NVIDIA GPUs. And NVIDIA offers two solutions like 2D comp, which is more general than the FFT, but indeed can be available for FFTs. And of course, it's only available on NVIDIA GPUs. cuFFT-MP is the NVIDIA solution for distributed FFT on top of NVSHA-MEM, and this one is of course available only on NVIDIA GPUs. To the best of my knowledge, the only library that supports the average GPU is the cuFFT, which is developed in the ECP project, ECP, and supports the CUDA and HIP and Shaker by internally having this implementation, each implementation internally. Our approach is Kokkos-FFT, and this one supports basically based on the Kokkos for the any parallelization port, and vendor support also offers the interface to the vendor FFT libraries, like cuFFT and rocFFT, for example. In short, distributed FFT is consisting of the FFT port and communication port and transpose kernels port. The most importantly, and the communications can be bottleneck, but at the same time, transpose kernel must be GPU ready, otherwise it will take quite a long time. So we need to make GPU ready kernels. The cuFFT offers performance portability by writing transpose kernels for each backend by hand. which is of course good if they might maintain, but it's kind of very difficult. The maintenance cost can be very big because of that. Our approach is different. We just rely on the Kokkos ecosystem to get performance portability for free. There are fundamental benefits with this approach. The performance portability first, the nice data structure as Kokkos views, and also for the very consistent build system on top of Kokkos. And so it is very easier to use in the Kokkos course. The fundamental difference between the eFFT is that if you try to use eFFT and couple with Kokkos, you need to write your own coupler between eFFT and Kokkos ecosystem. And each time you need to develop by yourself, but we offer it on top of our ecosystem. Brief context of Kokkos as a HPSF project, and here maybe we can skip this. But here, the most importantly, we need to make it vendor neutral. And here we have its own ecosystem like linear algebra and FFT and MPI and even more, and with tools. The key feature is single code runs everywhere, and nice data structure like Kokkos views, and nice parallelization for the parallel flow and for deduce and parallel scan, can be operated on CPUs and GPUs. Of course, and it's written in the Kokkos ecosystem and Kokkos papers. So now move on to our effort to develop the FFT library and its movement to the distributed version. So firstly, why Kokkos-FFT and who needs it? And as I said, and we are the one who need it. And this top right figure is the plasma turbulence simulation, but along toroidal direction we need periodicity, so we can rely on the FFT, and so we need it. So there are many legacy applications who like to put to Kokkos, which relies on the FFT libraries, like free simulations or periodic boundary conditions, for example. Or another example may be having a Kokkos code and waiting to integrate the in-situ data analysis using the FFTs. You can imagine spectral analysis or low-pass filter, for example. And this one is designed who will now get through the documentation of the facto standard FFT libraries because it's not necessarily easy when it's very big, but we still want to benefit from the powerful FFT libraries like FFTW or rocFFT and cuFFT or oneMKL, just as simple as numpy.fft. So as you can see in here, looking at the code snippets for dedicated FFT libraries, everything has their different APIs. And so you need to understand and you need to read documentation to develop an interface for that. In our API, we basically mimic the numpy-like FFT API, and we have the same name, but in the slightly Kokkosified because we also take into account the execution space, which allows us to make the compile time check to make it safer. The details is available on JOS paper in 2025. Last week we released the Kokkos 51.1, and there are a couple of key features. But it's fundamentally it supports the 1D to 3D FFTs up to 8D Kokkos views, and you can use batch FFT automatically. And it's quite simple APIs, and you only need to prepare big Kokkos views, just like NumPy arrays. And this API is much safer than using the raw FFT libraries because we don't need to access raw pointers directly. And many compile time or runtime errors for invalid usage, and so it's safer to use. And it supports the basic CPU backends and also for the non-experimental GPU backend like CUDA and heap and cycle. And by default, the FFT libraries dedicated to Kokkos backends are automatically enabled. And we support the Kokkos complex type and float and double, and layout left and right can be chosen. And we also we can manipulate on Kokkos default execution space and default host execution space. If you enable it, you can always use Kokkos Kokkos serial backend. We already have a couple of users internally, like the DDC paper, published by Tomapajiro in my colleague, and for JOS, and also for the GZ leaf, it's for the GZ gyrokinetic simulation we are developing, and this library is also using the FFT. Some different feature is the reusable FFT plan, which is kind of very important for the cuFFT or rocFFT, because actually the plan construction is more costly than FFT execution. And so this API is kind of unique because it doesn't exist in NumPy, but it's quite important because of the it can be very costly on cuFFT or rocFFT. The API is quite simple. Just you can construct a plan based on your execution space and Kokkos input and output Kokkos views, and you can execute FFT on different views, but you need to make it this same semantics, but you can use a different data pointer. But you need to make sure that the extents are consistent. If it's not the case, you have the runtime error. So it's still safe to use, but it can be very flexible. And this is quite an important feature for the realistic use case in the simulation. We have nice documentation compared to vendor library, in my opinion. The thing is that we have the copy-pastable example, which is compiled in each time in CI. And this API difference, and people don't often spend time reading carefully, but the example just copy-paste, and you have the copy button, and just copy it, and you can compile it and run it. And so it's quite easy to test, and you can compare that it is compiled correctly or not, and just checking the output is correct or not. So, and this kind of thing is very useful. So check it out if you haven't already. So that's our documentation. One example for a simple example and compare with NumPy, and it's as fast as the vendor libraries. The right figure is coming from the NumPy code. And as you can see here, it's kind of very clear and very simple. And just if you have from the inverse FFT and you're doing conversion in the space and do back and the forward FFT to back to the frequency space. The Kokkos version is slightly more complicated, but not much. And we can do the same operation on device without much difficulty. We have some benchmark program for two-dimensional Hasegawa-Wakatani solver using the conversion with FFTs and with 100 iterations without I/O. And we are solving actually some sort of physical problem. And the performance is whatever compared to Python. Of course, we have some acceleration. The most importantly, it works nicely on any GPUs. And also, the lines of code compared to Python version is just in the 1.5 times longer, which is kind of very similar in terms of length and the complexity. So we can write your code quite simple, not much difficult compared to Python version, but still it's kind of very performant and natively performant on GPUs, which is quite a nice feature. So let's now move on to the distributed capability. The right top figure shows the global architecture of our library. So this consists of these multi and the internal plans, but we are basically supporting so-called slab, one-dimensional decomposition, and the pencil is two-dimensional decomposition. And the shared plan is the embarrassingly parallel case. We also have the TPL plan, which supports calling the vendor native libraries like cuFFT and P. In the back end, we have the Kokkos and the Kokkos-FFT for the execution of the FFT and the Kokkos current port. And for communications, we have the multiple options like MPI and or device corrective libraries. In distributed FFT, you may imagine some sort of the pencil structure. If you say G pencil, it means that in here, all the data points are available along Z direction, but distributed along Y and X direction, as you can see in the green cube. On the other hand, Y pencil means along Y direction, everything is ready, but not for the X and Z direction. The same for the X pencil. The distributed FFT can be characterized by the transpose communication in between these pencils and do FFT along the dimension it is available, like G FFT for G pencil and Y50 around Y pencil, and things like that. So in here, we are currently supporting only the cuFFT MP as our internal TPL support, but we are planning to support rocFFT MPI or cuDecomp and the like in the future. So our API is quite simple and quite similar to the reusable FFT plan. We first need to create a FFT plan based on the execution space and Kokkos views, and just execute the plan. This is the shared API. The distributed FFT API is not that different. And we need to also specify the topology of the distribution because in the we need to know how the data are distributed. So we need to specify the topology of the input and output topology, and also communicator. It's most likely MPI convert. Maybe it can be sub-communicator if you are interested. And then you can use the execute the plan and on top of the for the distributed data. But this plan is designed to be reused for the forward and backward plan because in the internally we need to allocate buffers. So we try to reuse as much as possible. So this supports the forward and backward direction at the same time. And each data are already local, and we don't have any global data because it cannot be held by the single GPU. So only local data reside on the specific MPI run can be passed to the API. So implementation detail, we rely on the C++ dynamic polymorphism to select the four distinct internal plan types. The shared plan, as I said, is an alias to the standard API. It's no MPI aware, and just in the parallelization part doesn't matter. Parallelization can be made along the batch direction, which doesn't care for, it does not involved in the FFT API. And slab plan is the just one-dimensional slab decomposition, and pencil plan is two-dimensional decomposition, and TPL plans are interface to the vendor native libraries. From the viewpoint of routines, we have the all routines, and it's basically wraps the MPI communicator for global data transposition, most likely using the GPU-aware MPI all-to-all, or can be the vendor corrective APIs. And pack and unpack is the kind of unique procedure for the distributed FFT because we need to pack and unpack and the data to get ready for the all-to-all communications. And transpose is actually this is more like local transpose and to align data for FFTs. And then we also have the normalization, but it's kind of pretty optional. If you don't need it, you can do that manually, of course. And our approach is that in the make communications as simple as possible and make GPU kernels as complicated as possible because we have the expertise in GPU computing, so we can do whatever we want on GPUs. We have slightly less knowledge on the MPIs, and most likely the MPI communications matters. So we'd like to make it the fastest option, which is the all-to-all without any complicated API stuff, and just try to use the simpler or MPI all-to-all, wrapping the some API using views, but it's quite simple. As you can see, just calling MPI all-to-all on top of the view data, and all the complexities are handled on GPU on the other hand, right? This is the pack kernel, but we are doing some complicated stuff internally, but we have some expertise, so we are doing that approach. The same kernel is available for 2D to 7D views, and the parallelization is currently made with the MD range policy. And actually, we encountered performance issue, but which has been recently addressed by our team as well. So the benchmark problem, we are solving the three-dimensional Navier-Stokes equations. This is some sort of physical results, and the problem size is the 1000 to the 3, and we use the performance. We show the performance result in the next slide using the FP64, and we are calling the multiple and the C2R and R2C in the 4 ubiquitous steps. So even in the one-time step, we are calling the couple of the FFTs. And in the batch implementation, we can say that in the you just stack the velocity fields in a single 4-dimensional view, and this allows us to simplify the data and the code structure. and this actually didn't help in terms of performance, but certainly useful for the delta-F gyrokinetic simulations for plasma turbulence, where the two-dimensional batch FFTs are heavily used. The one thing to note is that this is the left side is showing our implementation for the non-batched case. You need to call the multiple times for the FFT library and the APIs on different velocity field around X and Y and Z. And we need to call the FFT APIs multiple times, which is no good. But in batched APIs, it's kind of simpler because then we can stack into the one for the view for the every velocity field, and which makes the implementation much simpler. This is the strong scaling result of this code up to the 2 to 8 nodes. And the number and the x-axis is the number of GPUs, and while it can be a number of processes because CPU are just using the same number of processes MPI ranks. And the y-axis is the execution time in the faster is better. And so the ideal scaling shows for the MI250X, and the measured one is showing the blue. As you can see, it's kind of nice scaling obtained for the MI250X and the ice break, but not for the 800 because it is already fast at the very beginning point. And at the end of the day, at the largest scale, 800 and the MI250X has roughly the same performance. On 800, actually, the MPI cost is roughly 90% of the total cost, so we cannot accelerate as long as you are using the MPI for this case. And this presentation, this slide shows the breakdown on each architecture, and the blue one is the all-to-all, and the red one is the transpose, and orange one is the pack and unpack, and green part is the FFT, and the magenta is the normalization. Something to notify is that almost always the all-to-all is the bottleneck on GPUs, but not the case for ice rake. And in addition, some sort of the GPU kernel is fully accelerated on the NVIDIA architecture, as everything is less than 20% in each case. But sometimes on the MI250X, and we have some slightly bad performance of the pack and unpack GPU kernels, which should have been addressed recently because of our optimization of the MD range. But overall, on GPUs, MPI all-to-all costs 60 to 90% of the total execution time. And pack and unpacking, at the moment I did this measurement, performance was not good, but recently still have improved quite a bit, and the perfect optimization should be made at the Kokkos 5.2 release. The CPU part, the all-to-all is still the kind of problematic, but it's less costly compared to kernels. And FFT still is kind of taking some time compared to the GPU, so there's still some room for the overlapping of the execution and communications particularly on ice rake, which is not the case on GPUs because your communication cost is dominant and there's small room to get benefit from overlapping there. We also compare the performance with kuFFT. I don't go for the detail, but it's coming, but this is from this X strap geometry to Y strap geometry FFT, and we also make a performance test on the PBC, and we have roughly the same performance for the 800 and the MI250X at the scale, which is good. But at the same time, it's slower compared to the kuFFT. And we found that in the kuFFT relies on the NVSHMM, and which gets the acceleration for the particular at scale. At first, we encountered a performance issue with kuFFT on 800 machine because in we have set the CPU binding incorrectly. You need to set CPU binding appropriately to make NVSHMM works correctly, which means that each process needs to access at least 2 CPU cores, which is kind of important feature for the kuFFT in my experience. But overall, it's outperforms our implementation, but not much. So it demonstrates that our implementation is kind of reasonable, and the performance is sort of very competitive. and it works on the NVIDIA and AMD and Intel GPUs and also for CPUs. We also try to discuss a bit about the distributed topology and batching impact. Something interesting is that in our 800 machine, we have the acceleration for the tensor decomposition for the 8x8. And because of this 8x8, one direction can be fully captured by the fully confined in a single node, and we have the acceleration by NVLink. So 8x8 is kind of the fastest on the 800 machine, which is not the case on MI250X machine because we don't have this kind of nice network there. And particularly on CPU, you found that in the some computational kernels are even slower compared to the FFT PERT. It's showing the orange, and green PERT is the computational total summation of the computational kernel, which is actually the bottleneck. And currently addressing the performance issue of AMD range on CPU as well, which hopefully will get merged and for Kokkos 5.2 release as well. Just a before final remark, and I'd like to talk a bit about our coming features, which is the batched APIs. And because in here, I'm also interested in I'm also working on the Kokkos kernel side, which has the brass and wrapback APIs in the batched sense in Kokkos kernels, which is extremely useful for some use case. And we are highly impressed by this API, so we'd like to try the same thing for the Kokkos-FFT as well. The basic idea is just in the coding small FFTs on device, like something like this. I just tried the basic FFT and IFFT, and still not need to implement real FFT and complex inverse real FFT, but it's basically should be the same thing. It's not as performant as vendor libraries, but it can be very useful for small FFTs, and you can improve data locality, and you can use kernel fusion, and including FFTs. So let me summarize this work and the future work. And we have the relative performance model libraries and dedicated for distributed FFT for the Kokkos ecosystem. And it can be very useful for some users who need FFTs and in legacy applications. And key features of Kokkos-FFT distributed is simple and safe interface thanks to Kokkos, and good performance on many GPUs, still keeping the reasonable performance on CPUs. And compared to the other libraries, we have supporting the very kind of unique features like batch capability, which is not supported by many libraries. Also for the vendor native distributed FFTs are supported, which should be promising in terms of performance. The future work include the better integration for GPU corrective libraries, even NVSHMM, which is promising in terms of performance, and also our improvement of Kokkos impacts our implementation tree, and the suboptimal default tile size and usage of registers has been addressed recently, and we can improve AMD range even more, and which brings us a better performance in the end. So thank you for listening, and so I'll be happy to answer your questions.
Thank you very much, Yuichi, for this great presentation. And indeed, we have time for questions. So are there any questions? You can raise your hand or open your microphone. Yannick, maybe?
Yes. 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 Thank you very much for this talk. It was very interesting. And I have a question. Does your distributed FFT include already in your package the transposition? It is completely automatic for the user. You just give the view and everything is done after.
Yeah, thank you for the question. Well, in our API, we internally construct a plan depending on your prioritization you made and the topologies you made. And we will do pack and unpack and whatever we need to perform the distributed FFT we need. So it's not visible for users, and we will do that on our side.
Okay, great. And the benchmark that you show us, yeah, we got roughly the same kind of behavior. The fact that, of course, the communication cost a lot. Do you think that the hardware between GPU, the communication between GPU in the future will be improved by a new technology, or then it will be good for spectral pseudo-spectral code finally?
Overall, communications are the bottleneck, but we have some good news from the viewpoint of the AI community. Because AI community recently are using the mixture of experts and of the AI LLMs, and this requires the all-to-all communications. So vendors now started to support natively the all-to-all communications, like Nico and Rocco do the support, and OneCCL as well. And also, Navier-Stokes provides the better performance in terms of communication cost. We have it's best still costly, but there is some room that in the performance improvement is expected in this kind of libraries developed by vendors for AI.
Okay, thank you.
And we are direct to develop this kind of API internally for the better communication performance. So. Yeah.
Thank you. I also see that Parikshit has the hand raised.
Thank you. So I was wondering if you could elaborate a little bit more about how you found that you needed those two cores when you were running into the performance bottleneck of cuFFT. Like, what told you that you needed to do this?
I think it's not necessarily needed related to the cuFFT, but it's more like NVSharing feature, and because cuFFT performs communication entirely with NVSharing, we need to set carefully. And actually, at first, and we have the worst performance of this cuFFT because we didn't set CPU binding carefully. But after that, after setting carefully, and the cuFFT outperforms more or less expected, but it means that in the NVSharing is a direction to go for us.
Thank you.
I also see that Evan has the hand raised.
Hey, first of all, awesome talk. This is sick. FFTs are hard, distributed FFTs are a pain in the behind, so I'm really impressed and excited about this work. I'm also an NVIDIA employee, so obviously I love seeing cuFFT MP is doing awesome, and I'm excited it's getting integrated. But I also come from scientific computing and still care about it, so everyone being able to do cool science faster is awesome to me. The proxy thread stuff, the needing two cores, I guess this is more of a comment after a compliment, is documented in the NVSHMEM documentation, but it is impossible to find in the documentation unless you already know it. So I'm glad that you could find it. I can confirm that, yeah, it's impossible to find. But it is a known thing. It's a host proxy thread that helps kick off network communications at still lower latency. The purpose is it's still lower latency than just having MPI do these things.
Yeah, thank you for the comments here.
Just saying you are not insane. It is confusing and it makes sense you had to have the second core.
Well, I just accidentally, NVIDIA people have contacted me and they helped me to resolve this issue because I myself cannot find the documentation because I didn't carefully do it. But they commented and it works actually nicely. So thank you for the help, because it's kind of difficult for me to find the appropriate one.
So we have a question in the chat. Guillaume, I don't know if your microphone is working. Okay.
Yeah.
So Guillaume is asking if there is any way to launch different FFT work plans simultaneously in order to overlap the communications of one FFT with the computation of a different one using two separate work plans.
This is a difficult and nice question, but difficult question to answer. From the viewpoint of the distributed FFT API, we can't do that for the moment because we wrap everything internally. But for the coupling with the conventional API for the non-distributed, it takes the Kokkos execution space, which ensures the asynchronism in FFT. I mean, everything is binded to the Kokkos, the CUDA stream internally. So FFT operations are performed on top of that stream. If you have multiple stream or execution space, you can have the FFT, asynchronous FFT. You can prepare for that. But you need to implement everything literally by yourself to that approach. But we may consider differently in the future. But for the moment, with distributed FFT API, it's kind of simultaneously.
Thank you. Any other question? Well, on my side, I have one. So you mentioned that you mostly use message passing, but for distributed FFT. But from what I understand, the NVIDIA implementation is using shared memory. I also see that there is the Kokkos project emerging nowadays. So there are a lot of way of communicating. Can you elaborate a bit more on what is the current situation and what you plan to explore regarding these aspects?
Sure. Because in the better performance cuFFT MP, my guess is the best option is relying on NV-ShareMem or maybe rocFFT for MD. And so we are highly interested in that feature and definitely we'll try that quite soon. And also the Nico and Roku thing and once share could be very promising because in the AI community needs it. So we may expect at some point that indeed they offer us a better performance compared to MPI. And if these corrective libraries are supported by Kokkos.com, I'm happy to drop the internal implementation and just use their implementation. But NV-ShareMem, I'm not sure the Kokkos and Kokkos.com supports it. So that part I'm not sure. If they don't support, I do that by myself.
I mean, in the Kokkos ecosystem, if you want to use shared memory, it would be more Kokkos remote spaces. So that may be also something to explore.
It's not maintained.
Yeah, the current status of the project is not completely clear to me.
Yeah.
Anyway, thank you very much. I don't see any other question in the chat. So maybe if you could switch back to your last slide. It was a very good introduction and transition to our next talk. So next month in Kokkos Tea Time, you will know better about the optimized MD range. We will have a talk by Adrien Tabernet about all the optimizations that have been integrated in Kokkos and that are currently being worked on regarding MD range. So yes, see you in 1 month as usual on the third Wednesday of the month, same time, same place. Thank you, everyone. Bye-bye.